Hello everyone. So my name is Huy Nguyen-Nano. I come from Sejong University. So today I want to talk about ballistic diodes for energy harvesting device based on graphene field effect transistor. So in this presenter, I will talk about graphene encapsulation, graphene ballistic diode for energy harvesting device, and how to make the sample, and in the result and discussion, I will show the ballistic diode performance. So now let's start with introduction. So as we know, graphene have very good silent transport, mechanical, thermal, and electronic properties. To improve the quality of graphene, hexagonal nitride can use for encapsulate graphene. Because of this, electric property of graphene can be improved very much. It has a very high electrical conductivity, high mobility, low noise, so it can use in the field effect transistor. Also, it can work at very high frequencies in the gigahertz or terahertz. So now look at in the basic graphene field effect transistor on the silicon oxide in here. By control the gate voltage, we can control the graphene Fermi level. It can be the electron transport or hole transport depending on the gate voltage applied. Now in here we have the very basic system in the life. It's called the ratchet system. It works only one direction. It's called for forward, so it cannot work in the backward. So apply the same principle, we make the graphene geometry diode. So in the forward, when the current pass from the left to right, so it will reflect in the graphene edges and pass through the net. Because of different geometry in the backward, electron will reflect and reflect light, and because this less current can be passed. So we call it the ballistic diode. For the workings with the conventional diodes, if made from the BN junction, it needs a threshold voltage to operate. So we can see this threshold voltage. But for graphene diodes, if working, it doesn't need a threshold voltage. My control graphene Fermi level gauge when the voltage is plus or minus, and the current direction, and the device can have the forward and backwards like this. It is opposite depending on the current direction and the gauge voltage applied. To have the ballistic transport, the device must have a long mid-free path. So also mid-free path must less than net width. So you can see here, this net width is the smallest dimension of the device. This is the size of ballistic device I will investigate in this research. It has the four devices, A, B, C, and D. For applications, ballistic diodes aim to optimize graphene rectifier for energy harvesting device. So you can hear the wireless signal can be harvested by the energy harvesting can be the energy can harvest by from the wireless signal through the rectifier. So now move on to fabrication method. So we use mechanical exfoliate for graphene and HBN on silicon oxide, and for HBN is to exfoliate on the BMMA. We also use the dry transfer method to pick up and make the encapsulate graphene. You can see this is encapsulate graphene were made. So to pattern the graphene, we use e-beam lithography in very high resolution. So you can look at in here, I saw the same image in the typical device A. It shows the narrow net width is about 0.1 to 0.2 micrometer. We also calculate the field effect mobility to estimate the mean free path. It's around 0.7 micrometer. So it means mean free path larger than net width. This is even for a device can work in the ballistic regime. So now in the result in discussion, I will show the ballistic transport for device A first. So now look at in this figure, I have the IV curve of device A in the electron transport when the gate voltage is less than 0, and hole transport when the gate voltage is less than 0. We also saw the nonlinear behavior from the IV curve. To evaluate the efficiency of the device, I calculate the rectification ratio. It is the ratio between the voltage measurement when the change in the current direction. If the rectification ratio equal 1, it means no rectification because I because of the linear behavior. If the rectification ratio is less than 1 or less than 1, the rectification ratio so for electron for hole because I because of the nonlinear behavior. Now in here I have the rectification ratio with difference of the gate voltage from minus 10 to 10 volt by the increasing of the current bias in the range of the 100 microampere. So we can see here this is direct point. So rectification ratio so highest value is near direct point for hole and the electron. So it's also increased by increasing of the current bias. So in here I have the rectification ratio by increase thing of the current bias in the 100 range in the fixed voltage. We can solve for electron and hole. So the rectification ratio increase linear by the increase of the current. Maximum for the whole electron is 1.22. For hole is 0.91. So it also means the electron has a larger rectification ratio than the hole transport. So now if look at is the device B and C, we have the ballistic transport. So it shows the nonlinear behavior for both device B and C for hole transport or electron transport. So in here we also see the rectification ratio also increase by the increasing the current bias for hole and electron. For device B, the last is rectification ratio at 1.32, and for device C at 1.626. And we also see the electron has the last rectification ratio than hole transport. Now in here I have the device D. So this is IV curve also shows the nonlinear behavior for electron and hole, and a rectification ratio also shows the different value by the changing the gate voltage. So in near direct point it shows the last is the rectification ratio. Now look at in this table, I show the highest rectification ratio for all devices A, B, C, and D. But let's focus on device C and D because it shows the last rectification ratio. We also compare our result with last published in the similar device C because our result shows the rectification ratio at 1.626 much larger than the previous published to compare with 1.31 and 1.4. Now I also compare the rectification ratio between four devices. So it shows the device D has the we compare the rectification ratio at the current bias of the 40 microampere because this value is quite low, but it can avoid the heating effect can be occur in the highest bias current. So in here we can see the device D shows the last rectification ratio at 1.58. So I think it's a good design for ballistic diode. So in conclusion, now I already saw how the device can be made and so the ballistic behavior of the absolute temperature for all devices. So it means ballistic transport can be optimized by changing the geometry And this research aims to optimize ballistic graphene rectifier for energy harvesting. So I finished my presentation. So thanks for listening.
Thank you for your talk. Do you have any questions? Please raise your hand. Okay. Yes, please.
Can you explain more details about gating?
Sorry, can you speak loudly?
Can you explain more details about gate voltage?
Gate voltage. So in here, because this is graphene field effect transistor, you know, by changing the gate voltage, when the gate voltage is positive, so the electron becomes the dominant. So transport in the graphene also is the electron transport. So, but when the gate voltage is negative, the transport in the graphene is whole transport. So because of this, in the working by control the gate voltage and the current direction, and the diode can be the forward in the electron or in hole. In the backward and the electron or hole depend on the current direction and gate voltage.
So the rectification you got is with the gate voltage or no gate voltage?
Gate voltage just for change the charge carrier. It can be hole or electron. But for rectification ratio, I apply the change the current direction. In the same value example, I apply 100 microampere plus and apply the minus microampere and measure voltage of the device and take the ratio to calculate the rectification ratio.
Okay, thank you.
Thank you.
Do you have other questions? Just a quick question. So is your film like strong enough to withstand from external stimulus? Like I was wondering, like your film HB and G is not like comparable with each other. Just wondering, like what interactions between HB and graphene.
Sorry, can you speak again?
So what do you think the interaction between HEM and graphene, is that like strong enough to external stimuli?
You mean to improve the graphene quality?
It doesn't have like any interactions between them.
No, HBN is an insulator. It can protect any impurity and some solvent from the EV lithography. So because I mentioned about the quality of graphene can be improved because it shows the high mobility and long mid-free path length.
So you just encapsulated HBN onto graphene.
Yes.
They are not just mixing.
Yeah, because the HBN only is an insulator. It will not apply to graphene because it has the highest band gap.
Okay. Thanks. If you have any questions, let's thank again Dr. Nguyen.
Okay.